So imagine that you some proof is ready, and then you have some formula P, and you are not able to write down with the proof of the formula because the proof in P is too long. But you know that such a proof exists, and in fact you're able to describe this proof succinctly. What does it mean to present something succinctly? So this is used in complexity theory often. Means that you do not represent the string as a string, but you take a circuit that computes bits of the string. Use the proof, but it's exponentially large, and therefore you have a circuit that computes bits of the string r. So this is good. So you have some evidence that P is true, logically true. But suppose somebody else comes and now says, okay, I have a succinct proof of some other formula, and gives you a circuit. So would you trust the person that is correct? Well, you get a circuit. It's something like having a code which you don't understand what it is doing, and then you don't know whether this circuit actually produces the correct proof. So this means that it's not enough to have a circuit that represents the proof, but we must have something more. We must be able to check that this actually, the circuit actually produces the proof. Now, Bianca came up with the idea that we should have another proof. This may be say in a different proof system. And this proof is now explicitly given. So let this proof be, say, sigma. And this is a proof of chi being correct. So now it seems that we didn't gain anything. So we wanted to have something else, not just proofs and proof systems, but we now have a proof in some other proof system. So can we get really a stronger proof system? The idea is to get a stronger proof system. And it turns out that we do get in this way something that is very likely stronger. So this is the idea of Krajicek, that an implicit proof will be a pair of proofs, a pair consisting of say sigma, a proof that circuit C correctly represents a proof in P. And the corresponding proof system he denotes by Q P. So this proof system is a proof system in which proofs are pairs, where C is circuit that should represent proofs in represent proofs in the proof system P, and sigma is a proof that does what it is supposed to do. because this has to be formalized. What is the pathology that sigma should prove about C? And that's a bit a complication. But in any case, what we can do is we can take P and Q equal and get sorry, this was supposed to be. Well, this is the proof system, and we have PEP, which he denotes by IT, implicit proof system of P. Now, the good news is that at least in some cases, implicit proof system at least in some cases, this proof system is stronger than P, or we have very good reasons to believe that it is strong. One reason is that he showed that if we take implicit extended, either extended Frege or extended resolution, then this is a proof system of the theory B12. And this is much stronger than theory S12 that corresponds to implicit extended frame, extended resolution. And we know that these are polynomially equivalent to extended frame. Now, one problem with this concept is that it is not very robust. We have to have a concept such that if we have a polynomially equivalent proof systems in the sense that they polynomially simulate each other, then if we raise this into implicit proof system or such a pair, then we get again polynomially equivalent proof. And this is most likely not the case. And in fact, this can be proved using the standard complexity assumption was done by Erfan. I don't have much time, so I will not talk about it. I was moving with if I have time for it, I will mention it, but probably I will not have time to talk about it.
Can you say again? This result?
So this is the result that I should at least state the result. So the result is that for two proof systems, and what we face is resolution and tree-like resolution, and consider that this proof, and this is not polynomial equivalent to resolution, and let's write the resolution delta, where this is a simple modification of the tree-like resolution proof system, which is polynomially equivalent to tree-like resolution proof system, but this just a kind of different presentation of this tree-like proof system results in the fact that these are not polynomially equivalent. And in fact, this is also an example where the same would work with the resolution. So we would have this implicit proof systems that in some cases the implicit proof system may be not much stronger or maybe even equivalent to the original. And this is something that I thought was not true. I thought that this operation P to going from P to IP was a jump operator, but it is not unless we somehow focus on some nice proof systems. But so far, I don't have a concept of a nice proof system for which I would be able to prove this.
It's unconditional or conditional?
Sorry, this is conditional.
Conditional on what?
It is conditional on okay, on X not being contained in G.
Do we have any evidence that we can't prove it unconditional then?
No, these are too strong things, so everything may collapse. So
Something follows from this non-equivalence. Yeah. From this non-equivalence, something follows. I mean,
so from this non-equivalence, it follows that the system is polynomially equal each other. Then it's not true that if you take this operation, that they will still polynomial.
yeah, I mean,
But what kind of other?
no, I mean, some. What is the evidence that we can't do that unconditional?
Unconditionally?
Yes. Why is it difficult?
Why is it difficult? It's difficult because it may happen that all proof system above say extended Frege are polynomially bounded. So then that they and they polynomially simulate each other. We cannot rule out this.
No, I mean specifically for a resolution.
Or for resolution.
But are those systems that you wrote there strong in a sense? Like how strong is when you say implicit resolution? How strong it is?
Yeah. So this is polynomial equivalent to.
Oh, I see. That's why it's probably difficult to. I see.
Yes. Okay, I will have to think about your question.
It's
Okay.
it's very.
So I was hoping I could say something about the proof, but I haven't even stated the theorem. And I still need definitions.
So from what you just said, even if you do effective P simulation, it's still not equal, right?
Sorry?
So from what you said, even if you do effective P simulation, they would not be equal.
Simulation?
Effective the Rahul and Tony's you allow the polytime algorithm.
I don't know. I haven't thought about it.
Okay.
All right, so this concept doesn't behave very well, and that there is another concept that introduced, and I will call it narrow implicit truth. In Jan Krajicek's notation, you have the same kind of operation that you take two proofs, two proof systems. But now this cannot be done for arbitrary proof system. So P has to be a proof system which is formula based. It's a proof system where the proof is not an arbitrary string satisfying some property, but it's really a sequence of some formulas. They do not have to be particular Boolean formulas, but it should be based on elementary steps. And then this is distinguished by this superscript n. Now it is again a circuit and a proof, but the condition on the circuit is that C computes formulas, not just the bits, but computes formulas. And these formulas may be encoded as strings. But since the size of the proof is the size of a circuit, and the proof that the circuit is correct, the formulas cannot be bigger than the circuit. Even the circuit has to output it. So you can view it as a implicit proof systems where you have restriction on the size of formulas.
So should we think of it as being like computed line by line, like the circuit is outputting the ith line?
Yes. So formulas or lines of the proof. But of course, we need a little bit more. We need also a circuit that would compute. So here you have an index of the formula in the proof, but you should also be able to compute from which formulas this formula follows. So that this will be mapping into the pair of indices which tells you that that a formula with index I follows from formula index J and index K, and perhaps also you should say by which rule it follows. So I have at least the definition, so I can now state the result. I still don't have all definitions. This is the case when you start motivating and writing definitions, and by the end you finish, it's over. So what I need moreover are quantified propositional calculi. So these are calculi that deal with quantified formulas. They're denoted by G, and this is sequence calculus. Operating with quantified propositional formulas. And the fragments of this calculus are GI, where the formulas are restricted to the level I. So there are also tree-like versions of this. But let me just say that these theories, these calculi correspond to particular theories And the important thing is that this corresponds to theory T through I. So finally, I can say that the result theorem is that we take resolution and GI, then it is polynomially equivalent to GI plus 1.
Should this be the narrow?
And this is, thank you, yes, the narrow was the, not narrow. Let me say a few words about the proof. I have very little time. So one direction is very easy, namely to show that GI plus 1 polynomial simulates this system. And this is because we can use this relation between theories and proof systems. So for this, we only need proof soundness of this proof system. E to I plus 1. And it's not difficult to do because you need just to check that you have the right amount of induction, and then you prove by induction that all the steps in this exponentially long proof are satisfied. The other direction is also natural, and it is based on cut elimination is a very important procedure in proof theory, in which you take a proof that uses cuts, secant calculus proof with cuts, and you transform it into a proof where you don't have cuts. But this is done gradually, so you eliminate cuts of the highest level, then you go to the next level, and next cuts, and so on. And at each step, this results in an exponential blow-up. But the thing that I did not realize until I started working on this is that the blow-up is only caused by, or maybe only caused by transforming the deck-like proof into a tree-like proof. And once you have a tree-like proof, then you can eliminate cuts without very much increasing the proof. And let me just draw one simple picture and finish by this. So the idea is, so we have an instance of a cut . And we assume that we already transformed this deck-like proof into a tree-like proof. So there is a subtree in which this formula is proved, this sequence is proved, and here is a subtree in which this sequence is proved. And what we do now, we look at the places where this quantifier was introduced. So these are places where we have some P, say, sigma, and from that we get this sigma, and places where the same thing is introduced on the left-hand side. So let's say gamma. The strategy of cut elimination is that we omit these cases of introducing a quantifier and just go on with the formula non-quantified. So as a result, we get something like and we say we do the same. No, on the other side, what we do is we use this sequence to cut it with this formula, and in this way we will just get the sequence without this formula. So this requires a number of changes in the proof, but let's just observe that what is one important thing, that this existential quantifier may be introduced many times, and therefore we would need to substitute, in order to be able to do the cut, we would need to substitute many different terms for paying. But in order to keep this proof small, we don't have to do this. We can take this sequence and substitute into this sequence different terms. And the substitution rule can be efficiently simulated in this calculus, so we can do it so that there will be some small subproof to get this t. And for each of these, we can do it. So as a result, this tree will become just a bag where for each of those we will have this premise and this, and so we will have errors a lot like this, and this will introduce cycles in the proof. It will be not a tree, but it still will be a bag, and there are a lot of things that have to be checked. I was hoping to tell you at least some of these, but half an hour is too little for questions. So thank you.
Thank you. Good questions?